Today we will start with various factors affecting vibrational frequency. Earlier we have done the various types of molecular vibrations. Now the factors which affects the vibrational frequency. So the factors are coupling interaction, then Fermi resonance, then hydrogen bonding, and then the electronic displacement effects. So these factors affects the overall vibrational frequency, that is the dipole moment of the molecule. So first we will start with coupling interaction. Coupling interaction is present as in the example of methylene CH2. It has two absorptions, that is it has symmetric and asymmetric vibrations. So there is a coupling interaction between them, that is asymmetric vibration always takes place at high wave number as compared to the symmetric vibration. As we already know, only the asymmetric vibrations are more important and they occur at high wave number, and so these are known as coupled vibrations because vibration occurs at different frequencies than that required for an isolated CH stretching. So coupling interactions takes place when methylene group to symmetric and asymmetric vibrations. These asymmetric vibrations are more important and they occur at high wave number as compared to the symmetric vibrations. So second factor is Fermi resonance. It occurs when the fundamental vibration, these are the fundamental transitions, when these fundamental transitions couples with these overtones or the combination bands, then the Fermi resonance takes place. And when the overtone or a combination of band has the same frequency to the fundamental transitions, then these bands appear very close to each other, and the effect is greatest when the frequencies match, and then the two bands are referred to as Fermi doublet, or we can say Fermi resonance. So when the two bonds share a common atom, as in the example of CO2, in this common atom, and it has two bonds, C double bond O, C double bond O, and this triatomic molecule now has two stretching vibrations. One is symmetric, other is asymmetric. The symmetric stretching vibrations produces no change in dipole moment, as we know earlier also, so it is inactive in the IR spectra. Only the asymmetric vibration, in which suppose one atom oxygen moves towards the carbon and the other away from it, then it will be a asymmetric, and in that case vibration will appear in IR region and it is nearly about 23-30 centimeter inverse. So in the triatomic molecules like CO2, we have again two fundamental stretching vibrations, symmetric and asymmetric. These symmetric stretching vibrations have no effect on the change in dipole moment, so they will be inactive in the IR spectra, but the asymmetric stretchings will appear in IR region and it comes near 23-30 centimeter inverse. So next is the hydrogen bonding. The hydrogen bonding gives rise to downward frequency shifts, as we have seen in UV spectroscopy also. It gives rise to downward frequency shifts, and in this, stronger the bonding, greater the absorption shift towards the lower wave number from the normal value. This is also expected, and generally we know that intermolecular hydrogen bonds are sharp and well defined, and these intermolecular hydrogen bonds are concentration dependent, and on dilution intensities of such bonds decreases and finally disappears as the number of molecules decreases, so the hydrogen bonding also decreases. As in this example, it is para-hydroxymethylbenzoate. In this, the OH group can be present at the ortho position or at the meta position, para position. If it is at the para position, then we will have these type of intermolecular hydrogen bondings, and if it is present at the ortho position, then there will be a intermolecular hydrogen bonding. Now the intermolecular hydrogen bonding has a stretching vibration at 1710 centimeter inverse, but the intramolecular hydrogen bonding will have at lower wave number, that is 1680 centimeter inverse. So generally intermolecular hydrogen bonding have the IR absorption at higher wave number and intermolecular have at the lower wave numbers. And so is the electronic displacement effect, and this effect also includes the inductive effect, mesomeric effect, configuration effect or field effect. 4 effects are included in electronic displacements effect: inductive effect, mesomeric effect, configuration effect or field effect. So under the influence of these effects, force constant, as we have already done in the Hooke's law in the starting, force constant or the bond strength changes and its absorption frequency shifts from the normal value, maybe increases, maybe decrease. So the interaction of alkyl group in the alpha position of CO group exerts inductive effect, which results in the shortening or strengthening of the bond. Consequently, the force constant increases, and so the frequency or the wave number of the absorption also increases. So these groups have their effects which affects the absorption frequency, and the inductive effects can be divided into 2 parts, mainly positive inductive effect and negative inductive effect. These effects, example positive inductive effect, example alkyl group, and negative group like Cl negative, Br, R should be small, I negative, OH negative. These groups are said to have negative inductive effect. So the alkyl groups which have positive inductive effect will increase the bond length. When bond length increases, then the force constant and frequency will decrease. And similarly, in groups with negative inductive effect, these group will decrease bond length, then the force constant and frequency will have opposite effect to the bond length, that they will increase. And then the mesomeric effect, it also works along with the inductive effect. In some cases, inductive effect dominates mesomeric effect and vice versa. And so is the configuration effect. It decreases the wave number of absorption. Configuration decreases the wave number of absorption. The oxygen atom of esters is more electronegative than nitrogen atom of amide. If we compare the ester group and the amide group, in the ester group COOR, oxygen is present. In the amide CONH2, nitrogen is present. Now, one pair of electron pair of nitrogen atom of amides participate more in conjugation, thereby decreasing the absorption frequency of CO group of amides. So in amides, lone pair of nitrogen is involved in conjugation, therefore the absorption frequency decreases. As shown here, in benzamide, CONH2 group is present. In that group, due to conjugation of lone pair of electron of nitrogen, the wave number is 1663 centimeter inverse, that is, it is less. And in case of ester phenyl acetate, it is 1730 centimeter inverse, it is more. So it's all about the various effects which factors which affects the vibration frequency of the molecules in IR region. So thank you.